This video is a continuation of the previous video, Jog Detector Design Part 2. The purpose of Part 3 is to present some results in the context of the jog detection problem as described in Part 2. Results in this video means graphs of probability of false jog indications as a function of missile range for various test cases described in Part 2. Test cases are defined by missile type, propagation model type, sea surface roughness, missile altitude noise, and frequency. Now, thus far, we have not concretely established the meaning of the probability of a false jog indication in terms of ECM effectiveness. That comes in Part 4. What we can say is that a false jog indication does not necessarily cause the countermeasure to fail. The effect of a false indication depends on the countermeasure used and on many other variables which are in play when the false indication occurs. Necessarily, the relationship between false jog indications and ECM effectiveness will be statistical. We can say that much. All of the data and results presented in this video and in Part 2 were produced by the Engage missile engagement application created by Sky Industries. Engage is not a commercial product, but a license can be had by a special arrangement if it's allowed by an export permit. Part 5, some results. One option here in this section is to show some or all results organized by test case, but this is a pedantic thing because there are a lot of test cases and it burdens the user or the viewer with the need to create a practical interpretation of several dozen graphs. And that's just too high a wall to crawl over. A better approach is to show just enough results to tell a story that describes the thinking process and then present some tentative conclusions. In this project, there are about 50,000 simulation runs comprising all the various test cases. These runs were processed for various jog detection power rate threshold values, because remember we have a very simple jog detector in this little demonstration study. It's pouched only on rate. The jog logic signal is true, while the measured seeker power rate is lower than the threshold value. And we're going to look at many different threshold values. This means that the analysis as presented here involved processing effectively just short of 3 million missile flyout simulation runs. This was done using 4 computers running continuously for a few weeks. It took a few months for the same computers to produce the simulation runs that are the input to this process. So let's take a look at the story the results seem to be telling so far. And let's start with the Sea Skimmer. The seeker operates at 9.3 gigahertz. The seeker activation range is 20 kilometers. The missile speed is 300 meters per second, plus or minus 10%. The missile altitude is 15 meters, plus or minus 3 meters. And it descends to combat altitude in 2 pre-programmed steps at around 9 kilometers and 3 kilometers. And the missile is guided in the azimuth plane only. Missile speed matters because it determines the power rate that the multipath causes. Since in this study, power rate is entirely due to missile motion. The temporal scintillation caused by multipath is assumed to be removed by signal filtering. So there's some signal conditioning has assumed to have been happened before the jog detector is used. Okay, so first let's look at results for the curved Earth propagation model with a glassy sea. And that means no wind and the largest amount of missile altitude noise. This is the case most likely to produce false jog indications because missile altitude noise can cause relatively high multipath power rates, which can translate to false jog indications depending on where the power rate threshold for jog indications is set. So here are the graphs of probability of observing at least one false jog indication as a function of missile range for power rate threshold from minus 10 dB per second to minus 70 dB per second in 2 dB per second steps. And here's the probability of observing at least 2 false jog indications. And 3. The basic idea here is to give a sense of the effect of the number of false jogs on the probability curves. And 4 false jog indications. Especially notice that as the number of false jog indications goes up, the probability curves for high fade rate get closer and closer to the ship. As the missile gets closer to the ship, for every jog detect threshold value, it is increasingly likely that the multipath will cause at least one false jog indication to occur. Now, for the minus 30 dB per second threshold, there's about a 50% chance of observing at least one false jog indication by the time the missile is 8.5 kilometers from the ship. This probably isn't the kind of performance that we want to see, regardless of the characteristics of the jammer that's using the jog detector. So let's see what happens if the sea surface is rough, so multipath nulls aren't as deep. As expected, the probability of false jog indication goes down. This is because the negative going power rates aren't as negative as in the glassy sea case. For a minus 30 dB per second threshold, there's about a 50% chance of observing at least one false jog by the time the missile is about 3 kilometers from the ship, instead of 8.5. Whether or not this is good enough is the subject of the next video. Now let's go back to the glassy sea case and switch from the curved Earth propagation model to the sea swell propagation model, still sticking with the sea skimmer. The main difference between these two propagation models is that the sea swell model allows for multiple surface reflections, so multipath nulls tend not to be as deep, at least until the missile is quite close to the ship. Then you have fewer, or possibly only one specular reflection point on the sea surface at close range. It's not surprising that the probability of observing a false jog indication is much lower in this case, but it is necessary to do the calculations to find out how much lower. The minus 30 dB per second curve hits the 50% mark at about 2.5 kilometers, but the graphs are much lower than the curved Earth model at all ranges. And if we switch from the glassy sea to the rough sea, still on the sea swell model, the minus 30 dB per second curve shows 0% probability of false indication down to 2.6 kilometers when it jumps to about 8%, where it remains until the final kilometer. So let's take a look at the high diver missile model, following the same presentation pattern as the sea skimmer. The high diver seeker operates also at 9.3 gigahertz. Seeker activation range is again 20 kilometers. The missile speed is also again 300 meters per second plus or minus 10%, and the missile altitude is 300 meters for all runs, and it's guided in azimuth and elevation. The missile is. So here are the results for the curved Earth propagation model in a glassy sea and the largest altitude noise case. There is a 100% chance of observing a false jog indication at nearly all ranges. This is because the high grazing angle and smooth sea cause power rates that trigger even the highest threshold at minus 10 dB per second. Anyway, that's not good. So let's see what happens if the sea surface is rough instead of glassy, so it's not as reflective. Astonishingly, there is now no chance of observing a false jog indication, even if the power threshold is set at minus 10 dB per second, so that's good. Now let's go back to the glassy sea case, but like in the sea skimmer case, switch from the curved Earth model to the sea swell model. It's a bit better than the results look a bit better than the curved Earth model, but only at long range. The minus 30 dB per second curve crosses the 50% mark at about 16 kilometers. For most of the missile's flight, it's pretty much a certainty that there will be at least one false jog indication, and that's not good. Now, looking at an overlay of many runs, 16 kilometers is about the range at which the first deep null occurs for the flyout geometry used in the high diver simulation runs. So that's the explanation there. Now let's see what happens if the sea surface is rough. For thresholds about minus 12 dB per second, there is no chance of observing a false jog indication. If the sea swell surface is rough, there is no possibility of a false jog indication for jog thresholds that are, most likely of interest in the real world. So it looks like the following story is emerging for the simple jog detector design, only for the test cases examined in this study. Anyway, if the simulations are correct, the sea surface conditions are important to the probability of false jog indications caused by multipath. And here are three broad conclusions. Point 1. For flat, smooth sea. If at the time of the missile attack the sea surface behaves like a glassy curved Earth propagation model, so everything is pretty flat on the scale of a radar wavelength, then false jog indications are expected for both the skimmer and the diver, and the situation is worse for the diver. Point 2. An undulating sea surface. If at the time of the missile attack the sea behaves like a sea swell model, and the surface is rough, so there are surface waves, a simple jog detector design based only on rate is sufficient, probably sufficient, since it is expected to produce no or almost no false jog indications for power rates that we would want to use in the real world to indicate a jog. Point 3, surface roughness. The more reflection points there are on the sea surface and the rougher the sea surface is, the less likely false jog indications are. So these are the broad brush 3 points we can draw from the story we've seen so far. Okay, so how do we pick the right jog detection threshold of all the ones we look at? If we know what power rates to expect from the jogs caused by the countermeasure, we could select a power rate threshold slightly above this, like more positive, and then pick out the false indications probability curve that applies. We just don't know which curve to pick yet. The key is the characteristics of the true ECM jog. Characteristics means the mean, standard deviation, and standard deviation confidence interval of the ECM jog power rate. For example, suppose we're using cross-pole jamming as a countermeasure, and further suppose that the polarization sweep rates and limits cause a mode 1 angle response in the seeker. And further suppose that this mode 1 response causes fade rates or power rates at the ship where we're measuring the seeker power of minus 40 dB per second plus or minus 10% variability with 95% confidence. Now, in that case, perhaps the power rate threshold should be set at minus 30 dB per second to detect the ECM, the signature of a mode 1 angle response. Now, once the power rate threshold has been chosen for recognizing jamming-induced angle errors, then the operating regime of the jog detector can be defined. It's defined by the engagement conditions under which multipath does not cause rates, power rates, that can be confused with mode 1 or mode 2 seeker angle deflections. And the word condition, in quotation marks, means specifically these things. Firstly, the missile speed and altitude flight profile. Secondly, the minimum range of the missile from the ship at which the jog detector needs to work. Thirdly, the sea conditions under which it needs to work. And fourthly, the range of radio frequencies covered by threats for which a jog detector is needed. Now, wiggling any or all of these parameters can change the graph of probability of false jog indication versus missile range, which is these graphs we've been looking at up till now. The operating regime is the combination of these 4 parameters for which the probability of false jog indication is sufficiently low, where sufficiently low means, well, we have to define that yet. In the case of cross-pole jamming, the same analysis needs to be applied to mode 2 and mode 3 angle responses if the jog detector needs to discriminate between these 3 angle response modes. And here is an illustration of the situation with mode 2 angle response, which is quite different from mode 1. And here's another key point. For different test conditions, we may require different jog detector configurations or even different designs to ensure that the detector's operating regime includes the real-world operating conditions, so the operating conditions where you need it to work. For example, as a first example, consider a jog detector whose intended use is in combat against a guided missile attack. Now, typically this might involve a high-speed missile or even supersonic missiles, both skimmers and divers in X-band, Ka band, and possibly Ku band. As a second case, consider air carry trials in which the aircraft necessarily flies at a slower speed and higher altitude than a real guided missile. It's possible and even likely that the aircraft will operate partially or entirely outside the operating regime of the 4-combat jog detector. Depending on the altitude and the speed, at long range the aircraft might operate within the detector's regime. In other words, the combat detector reliably detects jogs from the aircraft. That said, it might be possible to move the captive carry aircraft even farther into the operating regime of the jog detector, the 4-combat jog detector, not by flying faster, but by flying slower. What matters to the jog detector is the time rate at which multipath peaks and nulls are pushed through the jog detector's receiver. Peaks and nulls are spaced closer together by high altitude, so the only way to slow them down is through the jog detector, is to slow down the aircraft. Here's what it looks like. The missile flight is on the top, and a high-speed, high-altitude aircraft is below. See how much faster the peaks and nulls happen for the aircraft compared to the missile. Now here's a comparison of the same missile with the same aircraft, but the aircraft flies slower. The rate at which the peaks and nulls go through the jog detector is better matched. And a third difference, yet again, might be an anechoic chamber trial in which a real seeker is used, but multipath must be represented by an artificial model. If the multipath model doesn't match what the air carry tests provide, or what would be seen in a real-world combat, including missile speed, by the way, then a third jog detector is required. A fourth option might be a lab bench test in which the equipment is interconnected by coaxial cables. There might be a real seeker, but there isn't any free space radiation, so the ECM jogs must be artificially created by the software. And if those jogs are the same as what we see in free space transmission, fine. But if they're not, then you may need a different jog detector. If multipath is included in the coaxial cable test, it also has to be represented by a model like the anechoic chamber case. So you might need different jog detectors for different applications. It's worth mentioning that there are two versions of the anechoic chamber tests which blend into the coaxial cable tests. There is free space radiation in the anechoic chamber test, but not necessarily for both the seeker and the jammer. In the first version of the anechoic chamber test, which is uncommon, both the jammer and the seeker radiate in the chamber. In the second, more common version, the seeker does not radiate, so free space radiation only comes from the jammer. Now this means that the real seeker antenna pattern only applies to the signal received from the jammer. And since the seeker does not radiate into free space in the chamber, the real seeker antenna pattern is necessarily not applied from the seeker to the jammer. This means that the seeker antenna pattern in transmit mode must be synthesized and fed to the jammer through coaxial cables. So from the point of view of testing the jog detector, there may effectively be no difference between the anechoic chamber tests and the coaxial lab bench type tests as seen by the jog detector. Now this genuinely opens the door to some spectacular mistakes that can undermine not only jog detection, but also the legitimacy of the whole engagement simulation for both the coaxial cable and the anechoic chamber tests. For example, suppose that the two-dimensional antenna pattern is conveniently synthesized using an azimuth cut, a single azimuth cut, and a single elevation cut of the estimated or the known seeker antenna pattern. The two-dimensional azimuth elevation pattern must be synthesized by blending the azimuth cut and the elevation cut of the antenna patterns to calculate the gains at angles which don't lie exactly on the azimuth cut or the elevation cut at intermediate angles. The correct way to do this is by circularly blending the azimuth and elevation patterns, but this requires a bit of math, not much, but some. An easy way to sidestep the math, though, is just to multiply the azimuth and elevation patterns. For example, the antenna gain at 2 degrees azimuth and 3 degrees elevation is simply the azimuth cut, the gain of the azimuth cut at plus 2 degrees azimuth, multiplied by the gain of the elevation pattern at plus 3 degrees elevation. Just add the azimuth and elevation dB gains at those respective angles, and you're done. Now, this innocent appearing shortcut produces two-dimensional antenna patterns which have a rectangular artifacts in it because they're caused by the application of the azimuth cut at all elevation angles and the elevation cut at all azimuth angles. And the resulting 2D pattern does not represent the intended antenna pattern, which, generally speaking, has an approximately circular symmetry. Result is, if the target lies off the principal plane cuts, then not only is the signal that's fed to the jog detector wrong, the skin echo is also wrong, and it can be wrong by a lot. Anyway, the design methodology presented in this series of videos can be used for any or all of these cases. It doesn't mean there's no other way to do this, but this approach will work. Now let's look at the KU band seeker at 16 gigahertz. It's a C skimmer since at present there's no diver missile model available in Engage. So here's the probability of a false jog indication for the curved Earth model and a glassy sea, like we did before the other two times. Here's what happens if the sea surface is rough. Let's switch back to the glassy sea and look at the sea swell model. And here's what happens if the sea swell surface is rough. It's a similar story for the X-band seeker, but overall there is much less chance of a false jog indication. And here are the results for the Ka-band seeker for the Sea Skimmer missile. Here's a curved earth, glassy sea. Curved earth, rough sea. Sea swell, glassy sea. And sea swell, rough sea. And here are the results for the Ka-band high diver missile, starting with the curved earth model with a glassy sea. Curved earth, rough sea. Sea swell, glassy sea. And sea swell, rough sea. I'd like to make a few tentative observations, but I need to state some conditions first, which is the context that limits the statements. First point, validity of the simulation runs. Suppose that the simulation runs used in this study are representative of combat reality for the conditions that they are intended to represent concerning both the missile flight profile, including missile altitude noise as it's modeled, and sea surface conditions. Second point, signal conditioning. Suppose that the jog detector includes signal conditioning filters which effectively remove scintillation caused by, for example, sea clutter. If the seeker is frequency agile, then there will be scintillation caused by frequency changes, since multipath is a function of frequency. Suppose that the propagation noise caused by frequency agility has been removed by signal processing, either by filtering the aggregate power signal or by segregating the signal into frequency channels and then conditioning each channel separately before combining them for jog detection. For X-band, the operating regime of the simple jog detector probably does not include missile attacks in which the sea is mostly flat and smooth. A more sophisticated design is required for those conditions. On the other hand, if the sea is not flat, so it's undulating and a large scale in the sea swell scale, so there are multiple reflections, and if the sea surface is otherwise smooth, then the jog detector is likely to produce useful output over most of the engagement, possibly producing false indication when the missile is quite close. If the sea surface is not flat and is rough because of sea surface waves, then the simple jog detector is likely to produce reliable jog indications through most or all of the missile flight, all the engagement. For the Ku-band sea skimmer, the simple jog detector is unlikely to produce false jog indications provided the sea surface is mostly flat. If it's not flat, if there are sea swells, so there are multiple reflection points, the jog detector is more likely, strangely enough, more likely to produce false jog indications, but its performance may still be acceptable. Whether it is or not, we can't tell from these graphs. So that's the subject of the next video, how we go from these graphs to figuring out what threshold for jog detection is acceptable. Here are the results for all 8 test cases for the Ka-band missile, sea skimmer and high diver, curved earth and sea swell propagation, smooth and rough sea. The orange line in each graph is the probability of at least one false jog indication if the jog detection threshold is set at minus 30 dB per second. Now, we're a bit hamstrung in interpreting some of these graphs because we haven't yet established the meaning of the probability curves, except for one case. If the probability of false jog indication is 0, then the propagation doesn't interfere with whatever system is using the jog detector. For non-zero probabilities, the effect depends on the system that's using the jog detector, and we're not there yet. As a consequence, there's not much we can say about the sea skimmer except if the jog detector is based on a simple design, and it's based only on measured seeker power rate, then false jog indications are expected under effectively all conditions and at all ranges, for the conditions represented in this study. That's an important caveat. This supports the conclusion that a simple jog detector may not be suitable against Ka-band sea skimmer missiles. It's important to emphasize that this conclusion depends on the correctness of the propagation models and the way that the missile altitude noise was modeled. The situation is somewhat clearer for the high diver case. For a glassy sea, there are problems. But if there is any wind, if the sea surface is rough, whether represented as a curved earth or a sea swell model, then the probability of a false jog indication is very low for almost all of the missile flight. That's good. This supports the conclusion that a simple jog detector might be suitable provided the jog threshold rate is at or below minus 30 dB per second. Now that said, the truth of this depends on the meaning of even small probabilities of false jog indication, because for the sea swell model the probability is low, but it's not zero. Now suppose it's possible by remote sensing or some such other methods to determine whether the sea's surface is best represented by a single specular reflection point or a string of several reflection points. Suppose further that the same remote sensing could estimate the sea surface roughness based on the wave height, wind speed, or if either can be known or estimated. Alternatively, suppose that the remote sensing could be used to estimate, for example, the depth of propagation nulls from, let's say, 3 to 5 kilometers from the ship. This might be accomplished by measuring the signal from a drone fitted with a beacon, or by a weather report which includes wind speed, or an anemometer aboard the ship, or by an AI module studying a video feed showing the sea surface in the vicinity of the ship. Wherever it comes from, if this information is available or can be synthesized, it might be helpful to provide it to the jog detector with two inputs. The first input is a toggle switch between the curved earth propagation model and the sea swell model, whichever one the remote sensing indicates as most closely approximates the current propagation conditions. The idea is just to tell the jog detector which model is most likely applicable so that we can attach a confidence to the output. The second input is a quantitative indication of the sea surface roughness as a proxy for sea surface reflectivity. Now, alternatively to either of those two inputs, a single input might be provided, which is a proxy for propagation null depth, a single number which represents the combined effect of surface reflections and surface roughness. These inputs could be used to adaptively adjust the jog indication power rate threshold or other parameters in a more sophisticated jog detector. It might then be possible to define the jog detector operating regime and to apply or attach a correct confidence assessment to each jog indication for use by the system which uses the jog detector, for example, a cognitive jammer. And there's another possibility regarding additional inputs. Suppose two receive antennas were used instead of one, with one antenna above the other. If they are sufficiently separated and if the signals are processed non-coherently, then the measure of the power rate, seeker power rate, of the combined signals is expected to reduce even for flat sea conditions. It looks like this. Here is the A-scope application again, showing only power versus range for a constant altitude X-band missile. Now let's add seeker power rate to the display. In this case, the jog detection threshold is set at minus 30 dB per second, and any rate that is lower than this causes that segment of the rate display to be colored red. Now let's add a second receive antenna co-located with the primary receive antenna, so they're both at the same height. Now, since there are two identical antennas, the power goes up by 3 dB, but the power versus range doesn't change because they're both at the same height. Now let's separate the two antennas and watch what happens to the seeker power rate and level as measured at the ship. Now let's look at what happens if the wind blows. Now let's take a look at what happens if we change frequency. Change wind speed. Change frequency. Change wind speed. Back to X-band, change missile height. Change wind speed. Change antenna separation from 1 meter to 0.7 meters and change missile height. The second antenna might not be part of the jammer. The signal might come from the ship's ESM system or some other already in use system that can detect and track the seeker pulse train. The improvement to the jog detector reliability could be considerable. The question is how vertically far apart the antennas need to be, and whether the resulting elimination of false jog indications provides a sufficient improvement in ECM effectiveness to warrant the investment. Now, Engage can answer this question, but I haven't investigated that yet. Let's wrap this up with some quick summary statements. These statements only apply to the conditions and the models used in this study, and for a simple rate-based jog detector used against a generic sea skimmer missile and a generic high diver missile. The results are the output of a methodology described in this video and elsewhere, comprising an extensive campaign of simulation and analysis. And these conclusions are not intended to be the final word on the subject. They're intended to encourage a deeper examination of this problem using this methodology or some refinement of it. So here's the summary. Let's start with the bottom line. Sea surface shape and conditions matter to jog detection, and so does the attack geometry. And all of these results depend on how accurately the missile lofting and sinking dynamic, which is described in the video, has been modeled. There is no information on this subject, and it is probably the single biggest driver of the results that we've seen in this study. A jog detector has an operating regime. The regime is the set of conditions under which the jog detector is unlikely to misidentify multipath as an ECM-induced seeker antenna jog. Now, the jog detector operating regime needs to be matched to the kind of tests that you're doing. Real-life combat, which is the ultimate test, or air carry tests, or anechoic chamber tests, or lab bench coaxial cable tests, or some blend of those. Each jog detector must be designed and configured so that the multipath that happens during the test is unlikely to be misidentified as an antenna jog. False jog indications caused by multipath, by the way, are not necessarily a showstopper. The effect depends on the system that's using the jog detector, and this study does not get into that part of the problem. Now let's summarize the simple jog detector performance for all the test cases in this study. X-band skimmer. For flat sea conditions, windy or calm, it doesn't matter. From this study, it's likely that a simple rate-based jog detector will sometimes misidentify multipath as seeker antenna jogs. But if the sea surface is corrugated by sea swells, and especially if there's some wind, then a simple rate-based detector is probably okay. X-band diver. If the sea is glassy and smooth, then forget it. A simple jog detector won't get you across the finish line, but if the sea surface is rough, you're good to go, most likely. KU band sea skimmer. A simple rate-based jog detector is probably okay, although the results are mixed if the sea surface isn't perfectly flat, like if there are sea swells, at which there probably are sea swells. KU band diver. There is no available diver model at KU band, so this case wasn't examined. KA band skimmer. Forget it, smooth sea or rough sea, flat sea, corrugated sea, doesn't matter. A simple rate-based jog detector will produce, by this study, false indications caused by multipath, false jog indications. KA band diver. If the sea is glassy smooth, forget it. But if the sea is rough, if there's any roughness, then a rate-based jog detector looks like it can get the job done. And a final point, from all this study and work, I'd say no one's going to be able to design a jog detector using trial and error. It is absolutely necessary to use science. And this concludes a brief presentation and discussion of the results for the design of a simple jog detector based only on seeker power rate.